This lecture is going to focus on the residual strength of sedimentary rock. One thing that often happens is that a clay will form and lithify over many years and form a clay stone, a shale, or a mudstone, or something like that. But something will happen to it where it will cause significant straining. It can go back to kind of being like a soil if you just break up those particles. You know, they lithify, get cemented together, but that can be undone. And so there are a lot of different ways that could happen. But anyway, if we imagine doing a test, like a direct shear kind of test like this, where we're just forcing a clay stone to fail along a prescribed sliding surface, we could plot something like the shear stress that we've imposed on that clay versus the displacement along the sliding surface. So very much like a direct shear test. And what we would find is if we started with intact clay stone, it would have a very high peak strength, right? It's lithified, it's like a rock. So you would come out way up here like this and reach this peak right here because the soil is dense, it's been bonded together, the particles are tightly packed. Once you reach that peak, though, now the particles start breaking up and you're undoing some of the lithification that has happened over all those years, and so it'll start coming down. And this particular kind of claystone will significantly lose strength and basically go to a residual state like this, where you get this kind of flattening of the curve. So over here, you're at the residual condition. Now, let's say that you took that intact rock and just completely remolded it, like jumbled it all up so that the all the bonds are broken, but the particle orientations are still pretty random. Well, then you would get like a normally consolidated kind of behavior, maybe like this with a little peak, and it would come down to a residual. So this one is called fully softened. Or you could think of it as being remolded also, but it's usually called the fully softened strength. But it will go eventually to the same residual strength. And so if we look at what's happening inside of the soil, or inside of the rock, right, the earth material, initially the particles are very densely packed. And if this blue line is our sliding plane, that blue line is going to cut through minerals that might be fairly parallel to the sliding surface, but also minerals might be pretty, you know, crossing over that sliding surface. So actually it has to come up here and then go down there and break that one and then come up here. And so the true sliding surface is not really a horizontal plane. It's having to go kind of through this tortuous path. And there's maybe a lot of dilation happening. So the soils, the particles are growing and loosening as it shears. And that's all happening right at the peak up here. And maybe the bonds between particles are also being broken. If you fully soften the soil, you pre-break all those bonds, and so it starts off weaker. And you know, maybe the failure surface is going to cut through there in a straight line. It might be a little bit of a kind of a tortuous path through there, but it's going to be much weaker and potentially much looser along that sliding surface. Then the thing that happens when we get to a residual condition is that there's been a large amount of deformation. The soil's just continued moving. And as it moves, all of the clay minerals tend to become parallel to each other, like little flat plates. And we end up with this condition where all the minerals are parallel to each other and you get a straight line right through the center. And that's as weak as the soil can be because there's no tortuous path. The minerals are all just parallel to each other, and it forms what's called a slicken side. So if you go to a site that's had a lot of deformation through a clay stone soil, it'll look very shiny because a lot of light reflects off of these flat minerals. And so slicken sides will be the sort of shiny material. All right, so if the slope has moved in the past, like if you know there's been a landslide here, which often is the case, we're having to either mitigate or figure out if we can accept the risk of building on a location that has had a landslide in the past, then a residual condition will exist on the sliding plane, right? Because it's moved enough in the past to reach this residual condition. And so you should assume that it could reactivate along that residual friction angle, usually if the water table, if the pore pressure conditions change enough to cause it. So you would use a residual friction angle in your analysis. The problem is that residual friction angle can be very low, sometimes as low as 6 degrees or so for some different kinds of clay minerals. So what might cause a slope to have moved in the past, right? It's really strong rock, it's intact. Like what's going to cause it to come all the way over this peak so that you come down this hill over to the residual again? You know, what if you loaded just up to there and unloaded? It wouldn't reach that residual condition, the slope wouldn't really move. So one trigger might be an earthquake, right? You've got a slope, maybe this is like a coastal bluff where here's the beach and the water, and here's a rock face like you might find in the Palos Verdes Peninsula. An earthquake can come along and shake it and cause the slope to go over that peak, and you might get a weak zone right there on what used to be a bedding plane. Maybe there's a very thin clay layer in there. Another thing that can happen is that, you know, horizontally deposited sedimentary rock layers are subsequently uplifted and folded and bent up. And when you bend those layers, it actually causes deformations to happen. Let me grab a book real quick, I'll illustrate it. All right, so here's a soil behavior and critical state soil mechanics book. So if you imagine taking a book and bending it like this, you can see there's slip between the pages, right? The length of the bottom is longer than the top, and you have to get slip between those layers. Well, that same thing can happen to sedimentary rock deposits. So if you have a lot of tectonic movement, you're in an active seismological region, you get bending and folding, and it can cause this residual friction angle to form. So there are cases when this happens. All right, let's move on to measuring residual shear strength. The best test device to do that is the ring shear test. And so the ring shear test is like a direct shear test because it forces the failure to happen on a predefined horizontal plane. The only difference is that the ring shear test is circular, so you can just keep deforming it as long as you want. You can keep rotating this ring shear device, so you can get big deformations, big enough to cause this residual condition to happen. So here's an example. This is from a paper by Scott Olson in the Canadian Geotechnical Journal, just an illustration of the ring shear test. Typically, the ring shear tests are this middle one, although I have to say I've actually never run a ring shear test. This is not one of my areas of expertise. But you have a soil sample here in the middle between these a fixed disc and a shearing disc, and then it rotates it and breaks it along the shear band. And you can put normal stress up here and measure that normal stress, and then you can measure the torque and the rotation and get a shear stress and a displacement from that, and then plot those together. All right, one thing about ring shear testing or any kind of residual strength testing, sample disturbance doesn't matter, right? We're always talking about how sample disturbance is a big deal. It makes the soil usually weaker, although it can strengthen soil too. And that's why we don't run strength tests on split spoon samples like the standard penetration test sampler or the modified California sampler. I should say we shouldn't run strength tests on those samples. Sometimes we do run strength tests on ModCal samples, which is really a bad idea, but we do it anyway. So what that means is we can run these tests on bulk samples. So you know, you can just go and get some soil and put it in a bag, and it doesn't even have to be, you know, in a tube or something like that. So one way that we've gotten these samples to test in the past is that we will send a person down in a bucket auger hole, which is, you know, usually a few feet in diameter, and they will find the spot where there's been slip in the past and sample some of that soil while they're down the hole in a cage. Usually it's a geologist who really understands lithology and can go down there and make, you know, judgment calls about where that sliding surface is and can get samples from there. Technically, you can use a direct shear device to measure residual friction angle. It's just not as good as a ring shear device because you can't get enough deformation in the one directional loading, and also the cross-sectional area in a direct shear device, it changes as it loads, so you have to account for that in computing the shear stress. Generally, it requires reversal of loading direction, and you load it back and forth, and just hopefully eventually it's like a polished surface. But it's much better if you can just keep loading it in the same direction, and all those minerals will become parallel. Maybe they're starting to become parallel, then you reverse load direction and they go back. So, you know, it's not ideal. It would be much better to use a ring shear test if you're going to do a laboratory test. All right, another great tool is that if you know that there's been a landslide at a site in the past, and you think you have a reasonable handle on the pore pressure conditions that accompanied that landslide, or maybe other loading conditions, an earthquake or something like that, you can back calculate a residual friction angle. Okay, this is actually better in a lot of ways than doing a laboratory test for a couple of reasons. The first reason is that a lab test only samples one little spot, and there might be variability in the mineralogy of the clay throughout the layer. So you might get residual friction angles that are different in different locations. You've only tested one little location of soil. The other good thing is that you're going to be using some sort of analysis tool, and you want to make sure your analysis tool is calibrated to reality. And so it could be that the number you have to put in your analysis is not actually the real friction angle because there's counterbalancing errors, but at least if you can get a friction angle close to 1, you have some faith that your analysis is reasonable, and you can then evaluate a mitigation strategy using that same model. A huge complication is knowing the groundwater location. Generally, slope movements, maybe the initial slope movement happens from an earthquake or something, or tectonic bending has caused this shear band to happen, but usually continued movement happens because of fluctuations in the groundwater table. If you're lucky enough to have groundwater measurements, that's great. You can use those. You'd have less uncertainty in your model. If you don't know anything about it, you're going to have to make some huge assumptions about groundwater location. It's a huge source of uncertainty, and so that's a problem with back calculation. All right, now one more thing that I'll talk about is that residual shear strength really is a function of mineralogy. If you have very flat platy minerals like a montmorillonite, those are going to have a very low residual friction angle, because when they go parallel, there's a lot of double layer repulsion and stuff like that. So anyway, it correlates very well with liquid limit, right? You don't need an undisturbed sample. It's not like we're looking at peak strength or something like that. It really, you could think of it like as an index property, just like liquid limit is an index property. So a lot of the time, people don't even do the laboratory testing. They'll use a relationship like the one shown here by Tim Stark and Ide, 1994. And what you're seeing is the secant residual friction angle on the y-axis. And notice it's down here. Some of them are as low as 6 degrees or even lower in some cases. And you've got liquid limit on the x-axis. So if you get out here to very high liquid limits, this would be like a montmorillonite clay, you get very low residual friction angles. This is maybe 5 degrees, 6 degrees, something like that. If you're back up over here, you get a steady increase in the residual friction angle. Notice that the correlation really is good here, right? This is less scatter than we usually see in geotechnical engineering. And then these CF numbers are clay fraction. So this would be clay fraction less than or equal to 20%. You get a correspondingly lower liquid limit and a higher residual friction angle. Notice 32 degrees is kind of a common critical state friction angle for sand. So as you get up to there, you're getting closer to a sand-like material, and as you get more clay, it drops off pretty quickly. So, all right, so these are different clay fractions here, there, and there. A lot of the time we'll be using this one down here because we have a fairly high clay fraction in our soil. And then the 3 different lines are for different effective normal stresses. So the higher friction angles are for 100 kPa vertical stress. The middle one is for 400, and then 700 is the lowest one. So as you increase normal effective stress, you get a lower and lower friction angle. The strength still goes up, right? We're not going to reduce the strength by adding effective stress, but the friction angle goes down. So what that implies really is that there's a curved failure envelope. And let me sketch it here real quick. If you were to plot a tau versus sigma prime and sketch more circles, you're going to get some kind of a curved thing like this. And there's different ways to handle this, right? One thing you could do if you know, so anyway, the slope of this line is less when you get to higher pressure, but the strength is always higher, right? Slope is higher at low pressure, but strength is lower. So what you can do is if you know that your failure is fairly shallow, maybe, and 100 kPa is a reasonable effective stress to use, you could come along and use this top line to get your residual strength based on your liquid limit. If it's a very deep one, 700 kPa might be more representative, then you should use this lower line. And what you would be doing is, notice that this says secant residual friction angle. So maybe this is 700 out here, you would use a secant line like that. Maybe here's 400, you would use a higher number, and then 100 is here, you'd use a higher number yet, right? And I've exaggerated things a little bit in this slide just to illustrate the concept. But anyway, that's residual strength, and see you later.